Hello viewers, in the last few programs we had discussed about the VI characteristics of some very important thyristors such as silicon control rectifier, SCR, DIAC and TRIAC. In this program we are going to verify the VI characteristic of another very important device known as the uni-junction transistor, that is UJT. This is a setup before you. With the help of this setup we are going to verify the VI characteristic of the UJT. But before we actually do the experiment, let me explain you little bit of relevant theory regarding UJT. Now if I symbolically draw a UJT, the diagram will be like this. There are three terminals. This is base 2, this is base 1 and this terminal is emitter. This is the diagram, symbolic representation of a UJT. And if I compare it with a bijunction, that is bipolar transistor, if I draw its layer diagram, the bipolar transistor could be either a PNP type or an NPN type. Here you find that the terminals are emitter, base, collector. Here also emitter, collector and base, of course this is collector. Now if I see here in these type of transistors, that is bijunction or bipolar transistors, you have two junctions clearly visible, J1 and J2, but in this case there is only one junction, so this is known as the uni-junction transistor. The symbolic representation of a PNP transistor is like this. This is cause base, this is emitter and this is collector, and an NPN transistor is like this. This is emitter, this is collector and this is base. So clearly it is indicated that the difference between the two is this UJT has only one junction, hence it is known as uni-junction transistor, and these are two junctions, that is why they are known as bipolar or bijunction transistors. Now if I see a little bit of construction of this device, let me draw its constructional diagram, it will be more clear to you. The construction looks like this. Place it a little bit down. The two terminals are coming here. This is B2, this is B1. This point is say C, and here you will find diffusion of P type material. Of course this is N type of silicon material, and here at this junction we will have the third terminal, which is emitter. Now it is clearly indicated from the construction that the same base, this is the base which is of n material, this is divided into two zones. This is zone 1 having a resistance of say Rb1, this is zone 2 having a resistance of Rb2. Now since it is a semiconductor silicon material, this will have very high resistivity, and its resistance is usually from 4K to about 12K value. Now when a p type of material is diffused in it, a junction is formed, and from that junction another terminal, which is emitter, is taken out. So this is the construction, and the geometry of the device is such that it is distributed or divided into two zones of resistances having resistance 1 of zone 1, resistance 2 of zone 2, and from this zone, that is zone 1, we have one base terminal, we call it base 1. From zone 2 we have another base terminal, we call it base 2. This is the construction. Now suppose I give a supply between B2 and B1. Now B1 and B2 is known as the interbase terminals. So total resistance between B1 and B2 will be Rb1 plus Rb2, which is known as interbase resistance. So interbase resistance, say Rbb is equal to Rb1 plus Rb2. And if I give a supply between B2 and B1, that will be known as interbase supply, BBB. If I give supply in such a fashion that B2 is made positive, that means positive VBB is applied at B2, and this is of course either grounded or minus of the supply is connected here. In this case what is happening here is this device will act as a potential divider, because a potential difference is connected across the two and it has two resistances Rb1 and Rb2, so it will be acting as a potential divider. And what will be the current through the device? The current, say IBB, will be equal to the supply voltage divided by total resistance RBB, which is nothing equal to VB upon Rb1 plus Rb2. Suppose this is equation 1. This is the value of interbase current or IBB. Now what will be the voltage at this point C? Suppose that is Vc. That will be equal to nothing but this current into multiplied by this resistance. So Vc will be equal to IBB into this resistance Rb1. This is say equation 2. Now if I substitute the value of IBB from equation 1 into equation 2, what do I get? Substituting the value of IBB from 1 in 2, we get Vc equal to, in place of IBB I will write VBB divided by Rb1 plus Rb2 into Rb1, or this can be written as Rb1 upon Rb1 plus Rb2 into VBB. That means this is silicon, and hence we get, in place of Rb1 upon Rb1 plus Rb2, this factor is known as intrinsic standoff ratio. Intrinsic standoff ratio is defined as the ratio between resistance of zone 1 and the total resistance of the device. So if it is written as say eta, then it becomes Vc is equal to eta times VBB, where eta is intrinsic standoff ratio. This equation is very, very important, and it tells you that the potential at this point C, where it is divided into two zones, depends on two things. One is intrinsic standoff ratio and the other is the interbase supply. As I increase the interbase supply, Vc will also increase. Now how about intrinsic standoff ratio eta? Since it is the ratio between Rb1 and Rb1 plus Rb2, we see from here that the denominator is more than the numerator. So it has to be less than 1, is always less than 1. That means it is very clear from this equation that Vc is always less than VBB. Is it clear? So I say that the potential difference at this point C, the voltage at point C, will be always less than the interbase supply applied between B1 and B2. Now the two things on which this depends apart from VBB is the spacing of this terminal emitter between B2 and B1. Where is it spaced? That is very important. It will depend on that. And second thing it depends on is the construction of the device. Now if I replace this N material by P material, suppose here we have in this we have the N type of base. Suppose I replace this N type by a P type material and I diffuse N material in place of P, the same device will become a complementary UJT. Complementary UJT. So what is a complementary UJT? The complementary UJT is that device which will have P type of base and N type silicon diffused in it. Now what is happening when I am giving this supply? You see the potential Vc will be obtained here, and that will be given by this equation, and it will depend on VBB. It will also depend on spacing of the two, and it will also depend on the construction of the device. Now suppose I give a supply separately at this point emitter from external supply. What will happen? You see this is P type material, this is N type material, and this is a junction. So what type of junction it is? It is nothing but a PN junction. It is a PN junction, and that is nothing but a diode. And that diode will only conduct when this terminal, which is emitter, is forward biased. That is, it is positive with respect to this terminal. Okay. So that will only happen when VE, if I give a supply voltage VE here, then VE must be greater than VC. Unless VE is greater than VC, this device is not going to conduct because the diode will not be forward biased. Let us see when I give a supply here. Suppose I give a supply here VE and this point is grounded. What will happen? Let us analyze it. I have given a supply externally which is VE. Now if there could be two conditions. Condition 1 is when VE is smaller than VC. What is happening now? Since VE is smaller than VC, that means this diode, this PN diode, is reverse biased and the diode will not conduct. There is a possibility, there is a tendency of current flowing outside this device. In that condition, when the diode is reverse biased, the diode will not conduct, that means the device will not conduct. Only thing is little bit of current will try to flow outside the device. So that is the condition when VE is less than VC. So we can say the device will not conduct. Now let us see the second condition when VE is greater than VC. In this condition, it is clearly indicated from here that when VE is more than VC, this diode becomes forward biased and it will start conducting. Now when it is forward biased and starts conducting, what will happen? In this p type of material you have positive holes as charge carriers, and here you have negative electrons as charge carriers. So these positive holes will drift inside and they will make positive hole negative electron pairs. Now there is a question, this positive hole coming out of this p layer may go to B1 or it may go to B2. What is happening here is, in B2, at terminal B2 we have connected plus VBB, and this VBB is more than VC, it is also more than VE. So naturally this terminal will be more positive, and hence this positive charges, positive holes or charges, they will not be attracted by B2, but instead they will be attracted by V1. So it is very clear that when this starts conducting, in this condition VE greater than VC, the diode starts conducting. At that moment the positive holes from this p layer will start drifting towards B1. That is why this arrow has been given towards B1 and not towards B2. So it will drift towards B1. So conducting starts taking place, and what happens is they make electron hole and positive hole pairs. So resistance will reduce, further it will reduce, and naturally the conduction will hold, it will remain continuously conducting. So this is the condition when VE is greater than VC. So if I see it, the characteristic form, what do I see is like this. I draw the characteristic. You will find a characteristic like this. Of course this is voltage, this is current, and here in the beginning what is happening is there is a negative current. You see this is the negative current, and this area or zone where negative current is flowing, actually practically there is no significance, but theoretically it will happen. I told you that the current will try to flow out of the device. So this is the zone where current is trying to flow out, and it is negative current. We call it saturated, this is known as cutoff state, where there is no conduction of the device. Now at this point, which is known as peak point, the corresponding voltage is Vp, which is peak point voltage. Suddenly the diode becomes forward bias, that is V is greater than Vc, and it starts conducting. From this position to this position, that is this zone, it starts conducting. But what you are seeing here, the voltage is reduced, the current is increased. So from here to here it is negative resistance zone, and at this point you will find that the voltage has become constant. Further it will not reduce and it will remain constant. This point is known as valley point, and the corresponding voltage is known as valley voltage. This is valley voltage, and this zone is known as saturated region or saturated zone. So I will repeat, there are three states of conduction. Number one is cutoff state, when the device was not conducting at all, there is leakage current, and that is negative leakage current. Number two, it starts conducting at this point which is known as peak point, corresponding voltage is peak point voltage, but it conducts in a negative resistance fashion, and this zone is known as negative resistance zone. And of course corresponding current, you can say, although this is very small, this is known as peak point current. Although name is peak point, the value of the current is very small. So you have negative resistance zone because the voltage droops, and further at this point the voltage becomes constant. It will not go down anymore and it becomes constant, and that is known as the valley point, and the corresponding voltage is valley voltage. After that the voltage is constant. So that zone or region is known as saturated zone or saturated region. So this is the working, the VI characteristic of a UJT. Now here you will find the resistance. If I say that this arrow is near to B2 or B1, you will find that when it is non-conducting, the resistance between E and B1 will be more than the resistance between E and B2. I can say R EB1 is greater than R EB2. This is the condition when it is not conducting. But once it starts conducting, the resistance of B1 zone becomes lesser. So conduction starts in the B1 zone and B2 is more. So it is the opposite. That means REB2 will be more in case when the device is conducting. So this is all about your VI characteristic of a UJT. As I explained you, it has 3 zones. Number 1 is cutoff state or cutoff zone, number 2 is negative resistance zone, and number 3 is saturation zone. Now the same characteristic we are going to verify with the help of this setup. So this is the setup before you for verifying the VI characteristic of UJT. As you see, we are going to use 2 power supplies and 3 multimeters for doing this experiment, and of course this is the main board which has the required circuit fabricated in it. Now let me first explain the circuit. This is the main device, which is the UJT, and you see 2N2646 has been used here. Now before I actually perform the experiment, let me explain little bit of values about this particular UJT. You see, we are going to use 2N2646. You may also use 2N2647. These are normally found UJTs in the market, and then they have the peak point voltage Vp is equal to approximately 8 volts and the valley voltage is approximately 1.5. And for them the intrinsic standoff ratio eta is about 0.5 to 0.81. This is normally the value for this UJT, either 2N2646 or 2N2647. Valley point voltage is 1.5 volt, whereas peak point voltage is 8 volts. Now with the rest of the connections, let me explain you. As you see, these are the 2 terminals. This is the red one, the positive terminal, and the black one, the negative terminal. Here a constant 10 volt as VBB is to be given, which we take from this power supply. These are another 2 terminals. This is the red one, the positive one, the black one, the negative one. Here a variable power supply is to be connected from this power supply, and 0 to 10 volts are to be given. Across these 2 terminals, you see, this is the red one, this is the black one, an emitter is to be connected. So we are going to connect this analog multimeter as an emitter between these 2 terminals. Now between these 2 terminals, this is the red one, this is the black one, the positive and the negative, we are going to use this digital multimeter as a voltmeter, and this multimeter will be used later on when we want to note down the values of the current. So this is all about the board, and now I am going to connect it for you and perform the experiment. To start with, let me first connect the 10 volt power supply here. So the red will come to the positive terminal and the negative will come here. This is 10 volt power supply from this power supply, and this voltage, which is for VEE, will come here, the positive will come here and the negative will come here. So the 2 power supplies have been connected. Now let me connect this multimeter. Let me take it like this. This will go at the positive and this will go at the negative. So this analog multimeter has been connected here as an emitter. Now this voltmeter, for this voltmeter this positive will come here and this negative will come here. So this digital multimeter is being connected here as a voltmeter. Now you see there are two resistors here, one is 1.8K half watt and the other one is 47 ohms half watt. This resistor is meant for limiting the current and this is connected across B1 for getting the output. Now what these meters are going to read, of course these are the two power supplies. This will give a 10 volt constant power supply here and this will give a 0 to 10 volt voltage across these two terminals. This multimeter, analog multimeter of course, is being used here as an ammeter which will show the conduction of the device, and this digital multimeter is being used here as a voltmeter. It will read the value of VE. Now to start with the experiment, let me switch on the power supplies first. And here in this power supply, as you remember, I have to give a constant 10 volts. So let me use my specs, it will help me, and I am going to fix a constant 10 volt here. Constant 10 volts is being given here, and here I have to just vary the voltage in steps, and I will look at this multimeter. Please concentrate on this multimeter. Whenever there is a conduction, it will show a shoot and that will indicate the triggering of the device. So I am increasing the voltage gradually. You see, of course before that I have to put on this multimeter also so that it gives you the value of VE. Now I start, I am increasing it in steps. You see this voltage is also changing and it has not yet conducted. Yeah, you see a shoot is received here, and what does it indicate? It indicates that device has conducted. Now I again put it to 0. I will replace this multimeter with the help of this digital multimeter and use it as a meter. Why I am going to do it? Because I want to note down the corresponding values of the currents also. So let me replace this multimeter and connect this multimeter over here. So the positive will come here and the negative will be connected here, and again here the voltage is fixed, and again I am going to change the voltage in steps, note down the voltage here and the current here. Let me put on this power supply also, and now in steps I am going to change the voltage. Okay. So here it is how much? 1.052 volts. The current is of course very less. Here it is 2 microamperes. Let me note down the currents. For that I will need this pad. The voltage is about 2.4 volt. Okay, this is voltage and this is current, of course in microamperes. Voltage is 2.3 and the current is 1 microampere. Next let me change it. It is about 3.3 or 3.4, 3.39, so 3.4 volts, and the current is 2 microamperes. Then I change it to say 4.4 volts. The current is 3 microamperes. I further change it to say 6. It's about 6.7 volts. 6.7 volts, and the corresponding current is 5 microamperes. Then I will further change it to say 7.7 volts. The current is 6 microamperes. Now I change it to, here it is conducted, So let me take the values the value is, let me change this, yes, it is 3.994 and it was 7.9 volts there, 7.9 volts and about 3.944, say approximately 4 microamperes. So with these readings I can, of course I put it to 0, put it also to 0, and let me note down the values for you. With these values we can plot the VI characteristic. So the values are V volts and I in microampere. I will write it down. 2.3 is 1, 3.4 is 2, 4.4 is 3, 6.7 volts 5 microampere, 7.7 was 6 microamperes, and at 7.9 volts it was 4 milliampere. Now here you will find that from 7.7 to 7.9 volts there is a sudden jump in the current from microampere to milliampere, and suddenly there is an inrush of current. So it clearly indicates that at 7.9 volts the device has triggered. That means this is the peak point voltage and this is the corresponding current. Now here we can draw the characteristic like this with these set of readings, and you will receive a characteristic like this. You will not get this part which is imaginary or the cutoff state. We can get this part of the characteristic with this set of readings. Now you remember that in this experimentation I had kept VBB equal to 10 volts. I can change the value of VBB, I can change it to say 8 volts, 7 volts and so on, and repeat the experiment and get such readings. So we can get many such sets of readings, and many such sets of characteristics, UJT characteristics, can be drawn. So we draw a conclusion that with the help of such experimentation we can verify the VI characteristic of a UJT. So friends, this way we have verified the VI characteristic of UJT, and in the next program we are going to see a very interesting and important application of UJT known as the relaxation oscillator. Thank you.